Hi folks, we're going to review this idea of transforming functions right now. I'm going to start off with a fairly easy one that we've worked with. So say we take f at x equals x cubed. Now, in the past, if you wanted to see what the shape of this graph would be, only option really would have been to create a table of values, sketch the point, and hopefully get a sense of the shape of the graph. So you'd pick a few easy x values, determine the y values, plot them, and when we do that, let's see what that looks like here. Okay, and these points aren't necessarily very indicative of the shape of this graph. You could sort of tell it's not linear, so your option here might be to start plotting more points. So here, let's put in 0, 0, and then you put in negative 1, negative 1. Okay, and you keep going. Maybe you zoom in here. Okay, and here it almost looks as though they're going straight through, like as in a straight line. But we're really not getting a sense of the shape of the graph. So you could just keep plotting more and more points. But that starts to get cumbersome, especially when you're dealing with a much more complex function than just something like x cubed. Of course, we know that when we actually plot this graph, okay, we have this curvature that we don't necessarily see by just plotting a few points. Okay, so what transforming does is it allows us a different way to sketch the graphs of these functions. Okay, so instead of just plugging in values into a function, what we do is we try to find patterns between similar types of functions. So for example, if we consider the function x cubed plus 2, okay, we saw that there was a pattern when we took a known function and we added a constant to it. Okay, and you did the investigation, you realized that this had an effect on this original graph of x cubed, which was to move it up by 2 units. Okay, then we took a look at a whole bunch of other things. What if you operated on the x component and you realize that this moved the graph to the right by 2 units? So here what we're doing is we're always making our comparisons to some known function. Okay? So for example, let's take something a little more complex. So let's say we have y equals 2 times x minus 3 squared plus 2. Okay? So again, remember that our goal is not to input values into this function here. Instead, what we want to do is we want to compare this to a known function. And first thing is to recognize which function that is. So here are my variable x, and at some point it's going to be squared. If I were to expand this, eventually I'd end up with an x squared. So the idea is to relate it to the function y equals x squared. Okay, the reason we do that is we realize that once we were doing these transformations, the basic shape of the graph did not change. So how do we connect this graph here to the graph of y equals x squared? Well, by using those patterns that we found. Okay, so we know that this x minus 3 will have shifted the graph to the right by 3 units. Multiplying the x squared by 2, we know stretches it, gives us an expansion by a factor of 2. And we know that adding 2 after we've done these operations will move it up by 2 units. Okay? So again, when I talk about finding points on this transformed function, we're not plugging x values into this equation. Okay? We're starting off with points on my original function, okay, and we have our designated representative points on our parent function, and we want to see what these numbers, okay, which we are now interpreting as transformations, what effect will they have on these points? Okay. Now, remember that not only did we determine the effect of each of these operations, we also saw that the order in which we performed them was important. Okay, so you have to perform the multiplicative ones first, okay, then the 2 additive ones. So I'm going to repeat this one more time. When we're trying to determine points on this new function, we are not inputting x values into this equation. Okay? So the fact that we have this bracket here has no effect on what operation we're performing first, because we're not inputting an x value and then evaluating an expression. What we're doing is we're starting with points on our identified parent function, and we are seeing how these points change as we perform the transformations that we identify. Okay, so in this case here, vertical expansion by factor of 2, a shift to the right by 3, and a shift up by 2. Okay, now this is what I call writing the equation explicitly. Okay, so this is a quadratic function, okay, written explicitly. Okay, another way to identify this function is to use our function notation. Okay, is to identify the parent function as x squared. So we can call that, say, f at x. Okay, and what are we doing here? Okay, instead of our input in this case here being x, we see that our input into the square is x minus 3. So we write our input in this way. So here it's x minus 3 that is being squared. Okay, then what are we doing? We're taking that input squared, we're multiplying it by 2. So we would multiply that output by 2, and then to that output we're adding 2. Okay? Now, let's say I take this function here. Okay? If I ask you to sketch the graph of this function, again, instead of inputting x values into this equation and then determining y values and plotting those points, I want to compare this function to some function I already have information about. And because I see the x in the denominator, what we're going to do is we're going to compare this function to a parent function, which is the reciprocal function 1 over x. Okay? And we want to identify what transformations are being applied to this function 1 over x. So what I'll do here is I'll just rewrite this. Instead of 2 over x minus 3, if I rewrite that as 2 times 1 over x minus 3, it's very easy now to identify our transformations. So here, instead of having 1 over x, okay, I have 1 over x minus 3. So the input into my function is not x, but x minus 3. Okay. Now, once I get this output, what am I doing? I'm multiplying it by 2. So that's how we represent multiplying it by 2. Okay. And then here, once I calculate that new output, what am I doing? I'm adding 2. So this would be the transformed function written in function notation. We see, in fact, it was the exact same transformations that were being applied. But in the first case, they're being applied to the parent function x squared. And in the second case, they're being applied to the function 1 over x. Okay, so just to recap, what we're doing here is we're trying to find information, particular, say, the graph of a function, not by plotting points, not by inputting x values into the equation, but by comparing the function to some known parent function, in this case here, x squared, in this case here, 1 over x, and determining the effects of these transformations on that function. Okay, that's it for now.